Science.
Alright, ladies and gentlemen, class recording has started. So, on Friday, we began to discuss the basics or the details regarding electric charge. So, first thing we talked about, electric charge comes from where? Where does electric charge come from? Subatomic particles. Joe, specifically which two, or Dwayne, specifically which two subatomic particles? Electrons and protons, right? So, we talked about that electric charge comes from parts of an atom. Okay? Then, we talked about some basics, like how much electric charge was there, right? We talked about the idea that protons and electrons basically have the same charge, just a different sign on that charge. Then we talked about how like charges repel, opposite charges attract one another, blah, blah, blah. Okay? Then we got into conductors and insulators, right? First, conductors. Two things that I would like you to know about conductors. First, what kind of elements generally make good conductors? Like metals. Like, do you want to go with the why do metals generally make good conductors? Or you want somebody else to take it from there? Yeah. Why do metals generally make good conductors? Gabe, go ahead.
Because they're not extremely reactive nor extremely stable, so they'll accept the electrons.
You're getting along the right track, but you're confusing a couple of terms. What are metals generally looking to do with electrons, Emma?
They're trying to lose the electrons.
Do they hold them real tightly? If they're trying to lose electrons, do they hold those valence electrons real tightly to the nucleus? No, not really, right? So what does that allow them to do, Emma, if they're not held real tightly?
Pass the valence electron around, and then it passes from each metal.
Good.
And then none of them want it. So
Right. That, we can pass those valence electrons from one to the next, to the next, to the next, because none of them really want that valence electron, so that allows electrons to flow easily from one to the other. Okay? You're on the right track, Gabe. You're just getting some terms kind of confused. Okay? Now, logically then, your insulators are going to be what kind of elements? More generally than just gases, your nonmetals, right? And also logically, right, why do nonmetals make good insulators? What are they generally trying to do with electrons?
they're trying to gain electrons, so when the electron is passed to them, they're going to keep the electron.
Right, they're not going to pass it along to the next one, right? The last thing we talked about was charging objects. Regardless of how we do it, what is the gist of charging? What is the end result when we charge something? Minga, go ahead.
Transfer of electrons.
Transfer of electrons, meaning that an object is going to end up with either more protons than electrons, or more electrons than protons, right? Regardless of how we do it, that's the end result. Okay? Good there? Okay. On Wednesday, I asked you to complete the last graphic organizer that was in your packet. And that graphic organizer asked you to compare three terms. All right. One out of these three, I'm assuming you knew before, right? Electric charge. And if you didn't know it before you did your graphic organizer, you should know it now. Okay? The other two, I'm assuming you guys probably aren't real familiar with. Electric force and electric field. So let's start off with the first section, right? What do these three things have in common? What did you write down that these three things have in common? What makes them similar? What's one thing that you wrote down from your reading of the last section? Doug?
They all distribute electricity.
They all distribute electricity. I'll give that to you. I want a little more detail out of that when we get a little bit later on, after today, but I'll give that to you. Okay? What are some other things that you wrote down maybe that these things have in common? Some other similarities that they might have. I mean, you guys all have things written down. Just read one. What did you write down as far as these things that they might have in common? This one's kind of hard. There's not a whole lot of things that these things have in common. other than they all start with the same word. Okay? But because of that word, what will they all sort of deal with? Maybe
Protons.
protons and electrons, right? So they're all based off of those parts of an atom, right? Okay, are we good with that as far as what makes them similar? Now, let's start getting into the unique qualities of these three things. What's something that you wrote down for the uniqueness of one out of these three things? Okay? What makes one of them unique from the other two? Anything. What good?
The electric field affects objects in the space around them.
Good. An electric field is the space around an object, and we'll talk much more detailed about that later on today. So the electric field is a space, an area around an object. Okay? Trisha, what else?
Electric field causes electric force.
Good. Electric field causes electric force. Excellent, Trisha. That's a good one. Okay? All right. What else? What are some other things that we found out about these three things that make them unique from one another? What else? Come on, a couple more. Okay. Trisha, go ahead.
I don't know if it's a proton or if it's just like a positive charge something, but like their fields will like go outward.
Good.
Negative on the road.
It could be a proton or it could be multiple positive charges, but the field around a positive charge goes away from it, whereas the field on a negative charge comes towards it, and we'll talk about that a little bit later on as well. How about force? What'd you guys write down for electric force? Mike, what's one thing you wrote down?
How big an electric charge is.
How big an electric charge is will affect that force. Okay? What else did you write down as far as electric force was concerned? And Trisha, not that I don't want you to answer, but come on, what else did we write down as far as electric force is concerned? Let's get this result.
Yeah. Oh, okay. I'm not now.
Alright. Paige, go ahead.
Oh, I'm not sure if it's right, but I just kind of skimmed through it, but
That's
it
good.
said it's like an attraction that pushes and pulls between objects.
So electric force can actually go two ways, right? It can do what to some objects? Push them together, or pull them together, or, sorry. It can pull them together, or it can do what?
Push them.
Push them apart. So it's actually sort of a two-way street. It can actually pull things together or push things apart, depending on the charges that are involved and stuff like that. Alright, is that good for starters? Alright. Paige, that was right, by the way. So. Alright, let's talk about forces between charges. I think we've all gotten. Good.
I didn't have the outline.
Underneath today's outline. Just go.
So for electric force, and the buckets that is necessary for life, it is the electric field causing electric force and then electric.
Technically, yes, although the field doesn't really do anything, it's more the force that does stuff. Alright. Settle in. Okay, so we'll talk about force first. Electric charges can cause changes in motion, which means that they exert forces on one another. And I think we've all gotten to the point where like charges repel, opposite charges attract. Okay, we're past this point, yes? Okay. So, how much force exists? How much force exists is calculated by something that we call Coulomb's law. Okay? First, Coulomb. That's a term that we've heard before, right? Okay? That's the unit that we use to measure charge, right? Obviously, this guy had something to do with this whole idea of, bringing electricity and force and stuff like that. Okay? Coulomb's law depends on a couple of things. I won't hold you responsible for using Coulomb's law to calculate stuff. You won't have to plug things into this equation and solve for the amount of force. But if we talk about what's in this formula, first, what do you think F sub E is going to stand for? It's going to stand for force, specifically force of, let's go electric, because that's the kind of, so it's the electric force. F stands for how much force is there actually existing in this situation, okay? Second, Q1 and Q2, they represent the charges that are either attracting each other or repelling each other, depending on what the situation is, okay? You gotta have two charges in order to have force, right? Because they either attract each other or repel each other. Okay? Any guesses on what D might stand for? Distance. Okay? So D is the distance between those charges. Okay? And then the last part is this K value. This K value is a constant value that we call Coulomb's constant. It's something that's thrown in there to make what our measurements are come out to what the force is that they're actually feeling. Okay? Notice that Coulomb's constant is a number in scientific notation, but it's also raised 10 to the 9th power. It's a pretty big number. Electric force is a very strong force. It can push and pull very strongly if the charges are big enough, right? Remember, Q1 and Q2, we talked about like the charge of an electron and the charge of a proton. Those were also numbers in scientific notation, but what was the exponent there for one electron? Does anybody remember? If you flip over that sheet to the other side, the numbers there. Okay. It's times 10 to the what? Negative 19. So there isn't a whole lot of force between like one electron and one proton, but if you get a lot of them there, then you start getting into some significant amount of force. Go ahead, Algebra.
Is the K capitalized?
K is actually a lowercase, but then the C is the subscript of it. So, all right, good there with what's in this formula. Okay. But more importantly, let's talk about relationships. First, where are the charges in this formula? That formula is a fraction, right? Where are those charges in that formula? Numerator. One-handed. If we make the numerator of a fraction bigger, what happens to the answer of that fraction?
It's bigger.
It gets bigger. So if we make these charges bigger, how much force will they feel from each other? More force, right? So that means that force is directly related to the size of the charges. Okay. Bigger charges, more force. That means they have a direct relationship. Okay. But where's distance in this formula? Denominator, right? If we make the distance bigger, if we make the bottom of this fraction bigger, what happens to the amount of force? Smaller. What kind of relationship did we call that? How about inverse? Okay. But notice, what are we doing to distance in this formula? We're squaring it. So the force is inversely related to the distance squared. Okay? This is the first example. Oh. No. This is the first example of something that we call an inverse square law. Okay? Because we see this a lot in nature, that the amount of force that exists between objects is actually inversely related to the distance, but not just the distance, it's actually the distance squared. Go ahead.
I was just wondering, on the PowerPoint it says the sizes of the charges, and on ours it says the amount of the charges. Is that just another way of saying the same
Yeah,
thing?
same thing. Basically, how much difference is there between the number of protons and the number of electrons in that object? So, back to this distance thing, right? If we start off with these two charges, and they're 1 meter apart, but then we move them 2 meters apart, What have we done to the distance between them? It's not a trick question. We've increased it by how much?
3.
It's doubled. It's twice as much, right? If we go from 1 meter to 2 meters, okay, that's double. But if we put a 2 in the bottom of this fraction, yes, what is actually going to happen to that bottom of the fraction? It's now a 4, right? So by taking the distance and making it twice as big, it's not half as much force. It's actually 1/4 as much force. We kind of saw this relationship earlier this year, dealing with what concepts? Do we remember when we saw this, Minga?
Energy.
With which energy specifically, Minga? Do we remember?
Kinetic.
Kinetic energy, right? Kinetic energy had a squared value in it, right? And we talked about that doubling the speed actually gives you 4 times as much kinetic energy. Same kind of thing here, except we're working in reverse because it's an inverse square law. Okay? Good there? But there's an important problem here. We know how much force is there, but the problem exists that these forces these charges aren't actually touching each other. They can apply force to one another even though they don't contact one another. And when we're developing these concepts and figuring out what's going on, that's a problem. So we have to come up with a way to fix that problem. How do these forces, how are they able to attract each other or repel each other even though they don't actually touch? And that's where we get into field theory. Okay? There are certain forces out there, gravity, electric charge, magnetism, that can actually affect the motion of objects without actually touching them, right? You experience the gravity stuff every day. If I drop this ball, what happens to it? It falls, right? Okay. Does the earth actually touch it in order to make it fall? No. So there has to be a way that that happens, that the earth can actually affect the motion of this object without actually touching it. So in the 1700s, a guy named Michael Faraday proposes what we refer to today as field theory. Okay? The fact that it's field theory should tell you what? It explains why things happen. So Michael Faraday proposes an explanation for, at the time, what we referred to as something that we called, quote-unquote, action at a distance, which is another way of saying motion without touching. Okay? The telekinetic field. So what Faraday says is that there is an area around an object where it can affect the motion of other objects. This space around a charge where it can affect other charges. And we refer to this area, this space around the object, as the force field. Okay. Here, in this classroom with this object, this ball, okay, gravity can affect its motion, right? Pulls it this way. Because this area is affected by the gravity of the Earth. So we are within the Earth's gravitational field, the area in which it can affect the motion of other objects. Does that make sense? Okay. There's area around these positive and negative charges where they can affect the motion of other objects. For instance, down at the bottom of your page, you'll see that there's a couple pictures that didn't copy very well, and it actually turns out better that they didn't copy well. So, the first little dot, the solid dot on the left-hand side, is supposed to have a positive sign in it. That's supposed to represent a positive charge. Okay. As far as the electric field is concerned, we have to ask ourselves a question. And that question is, what will happen to a positive charge in this area? So in that first picture, right, that has a positive charge. If I bring another positive charge close to it, what's going to happen? They're going to do what to each other? They're going to repel each other. So around this positive charge, the field is a bunch of arrows pointing outward. Because if I bring another positive charge close to this one, they're going to repel each other. Okay? The second shaded dot, picture B, is actually a negative sign. So if I bring, once again, we have to ask ourselves, what happens to a positive charge? So if I bring a positive charge close to a negative charge, what are they going to do to one another? They're going to attract. So if these arrows around the positive charge represent the repulsion, what do you think the arrows around the negative charge are going to look like? Which way are those arrows around the negative charge going to point? They're going to point towards the negative charge. Because if I bring a positive charge in this area, it's going to be attracted to that negative charge. You might want to fill in those arrows, because the arrows actually were supposed to show up on the picture, but they didn't copy very well. So you might want to fill those in, right? So the electric field, the area around a charged object where it can affect other objects, is determined by what would happen to a positive charge. That being said, in general, we can make assumption about these arrows. Which way are the arrows going to point? They're going to point away from what and towards what? Clever.
Away from a positive charge and towards a negative charge?
Because it all comes back to this question, right? What happens to a positive charge? Positive charges are generally repelled by other positive, not generally. Positive charges are repelled by other positive charges and attracted by other negative charges. Okay? Is that good there? We're ready to apply some things? I know, applying things. Here's a positive charge. Here's a negative charge. Luckily for you guys, this is a picture similar to letter C on your on the bottom of that outline that we're working on right now. Okay? So I bring another positive charge in close here. What's going to happen to that positive charge? Good.
Is it going to be attracted to a negative charge?
So the field at that point in time would look something like this. Okay? If I move it right in the middle, what's that going to look like? What's going to happen there? Gabe, anything different?
The positives are going to repel and the new positive is going to attract to it.
Alright, so that's what the field would look like at that point. But, what if I moved it like over here? Bingo.
Push it that way.
Right? This positive charge, right, it's closer to the other positive charge than the negative one is. So in this case here, that field's going to look something like this. Okay? If I get it somewhere like, oh, not that one, here-ish, right? Still going to be repelled by this one, but it's going to be attracted by this one, right? So in that case, the field would sort of look something like this. If I bring it over this side, right, what are the lines going to look like there? Which way are they going to point, Joe? To the left. Why to the left? Right. It's going to look something like this. Generally, what do we see about the arrows? Where do they start and where do they head towards? Clever. Those arrows all start where? They point away from positive charges and point towards
Negative
the
charge.
negative charges, right? So that would mean that our picture This is the electric field around these two objects, because now they can both affect the space around them, right? But if I have two positive charges, right, none of the arrows point towards either of them. They all point away, because what would positive charges do in that instance? They'd all go where? Away. They all go away from that stuff, because they don't like to be attracted, right? In general, the lines move away from positive charges and towards negative charges. The electric field is going to head towards negative charges and away from positive charges, because we define it by what would happen to a small positive charge in this case. Is that good? Does this maybe clarify a little bit of what you read last week? I'm not sure if you, reading it, it was real clear, but. Alright, we good there? Yeah, good.
Okay, if positive charges repel each other, or like charges repel each other, then why are you drawing like lines from the positive charges going to each other?
Like what?
No, when you were like drawing those ones, like you drew one of the lines from a positive going to a positive. Like before you moved the one to the other side though. Yeah, that one.
In this case, the line represents what would happen to this little charge in this case, right? Technically, this one would probably move away as well, but we sort of define it as, okay, this is the field around this object. But that arrow is pointing away from the positive, right? Because these two would repel each other, so this object would move in this direction like that. Is that good?
Mhm.
But generally, what we would find is that eventually it would sort of loop back around and come back over on this side here. So, because eventually they start attracting, if it gets far enough away from this, it will start being attracted by the positive charge again and go there. Good? Alright. The next outline, the one that I gave you today, is a pretty long outline. So, I want to get started on the beginning of it before the end of class today, handle the first page basically, because a lot of it is some review and relating some old concepts to some new things. So let's get this first page done. We still got like 8 minutes, so it's not like we're rushing that much. Okay? But the new outline that we got today. Okay? All right, good here? So let's do this. Just go ahead.
Will the 20 on the quiz form?
No, this will not get in the quiz tomorrow. Just the first outline is on the quiz tomorrow.
This is such a happy car. I like it.
Just wait. This it gets happier.
Just like.
Yes. So this is not smiley face happy, but I mean just wait. So this green object down at the bottom, that represents the Earth. Okay? And then that's just some old object I made yellow. It's not actually the sun. Okay? Because it wouldn't really make sense for what I'm about to show you. But okay?
You can make it
Let's say this happens. Okay? So we take this object and we raise it. At the beginning unit that we did, we talked about the effect on the energy of this object. What would we say would happen to the energy of that object? What?
gain potential.
It gained gravity. Let's make sure we use the descriptive at this point. What kind of potential? Gravitational potential. Did we do work on this object? Yes. Joe, what was our definition of work?
To move or destroy stuff.
That's more energy. What's work? Linda.
Force and distance.
We need force and we need distance. What does work do to energy?
The transfer of energy from an object to another.
The transfer of energy. So when we do work, we change energy. Did we change the energy of this object by doing what we just did? Yeah, that's work. Okay? What happens to PG? It increases. Was work done on the ball? Yeah. If I let the ball go, right, what would we see happen from an energy standpoint? Not a trick question, Nate.
Well, it would lose potential gravitational, but gain kinetic.
It's going to lose gravitational potential, but at the same time, gain kinetic. Okay, good there? Alright. So, what happens to PEG? It decreases, kinetic energy increases though. Why do I bring this up? Because that object has changes in energy as we move it around in the Earth's gravitational field. Do you think there's going to be some similarities that we can draw when moving a charge in an electric field? And if you said yes, you'd be right. Okay? So, let's talk about electric potential energy. We talked about potential energy in the first unit. We spent mostly the time talking about gravitational potential energy, but we said potential energy is energy based on what? Potential energy is energy based on location or position. So, electric potential energy is energy due to its position within an electric field. Electric potential energy, EPE, is a form of mechanical energy. So all the things that we just talked about from the standpoint of gravitational potential energy will also be true with electric potential energy. When we move a charged particle within an electric field, we do work on it, and the energy of that particle is changed. For example, here's a picture that shows a large positive charge over on the left-hand side and a large negative charge over on the right-hand side. And there are arrows representing the electric field. Is that consistent with what we just discussed? Because the arrows are pointing away from positive charges and towards negative charges. Okay? Let's say I do, and this yellow sphere represents a positive charge, a different positive charge. Let's say I do this to it. Right? What can you tell me from an energy standpoint? What would have happened right there? Well, let's talk about what we know physically is going to happen. Does that yellow positive charge like that I moved it closer to the other positive charges? No. What is it going to try and do to those, or what is it going to try and do now that it's in that position? It's going to try and repel, right? Can I use that repulsion to do other stuff? Yeah, right? What is this the equivalent of when we talk about it from a gravity sense?
Raising the ball.
This is the same as me raising the ball from here to here. So what have I done to the electric potential energy in this case? I have increased it. So according to your outline, right, what can I do for letter D? It says, what can you do to increase the electric potential energy of a positive charge? How would you move it to increase electrical potential energy? What would I move it closer to? Other positive charges, right? But now, if I let this thing go, what's going to happen to it? Which way? It's going to move to the right, towards the negatives, away from the positives, right? What's going to happen to it as it moves away from the positives and towards the negatives? What happens to this ball when I drop it?
It gains kinetic energy.
It gains kinetic energy, as what happens as well?
It loses potential energy.
Right. Right. Electric potential energy decreased, kinetic energy increased, right? For letter F, what happens to the kinetic energy of a charge, or that positive charge, as it loses electrical potential energy? It gains kinetic energy. Is that good for basic concepts at this point? We didn't finish this up, but the bell's going to ring, so we'll finish this up tomorrow. Okay? Trisha, like you said, that stuff we just talked about, not in the quiz tomorrow, just the first outline. Okay? All right, buddy, have a good evening, and I will see you tomorrow.